Okay, today we're talking about tangents and chords. So if we're going to talk about tangents on a circle, we need to know what a tangent is. A tangent line is a line outside a circle that touches the circle at one point. And I have our circle already drawn. The dot in the center is just to show, hey, that's the center of the circle. So if I draw a line outside the circle that only touches the circle at one point, there is our tangent line, and it could go anywhere on the circle. I don't just have to do it on the left side. I could put one on the right, or the bottom, or the top. Doesn't matter where the tangent line goes, but if it touches one point, it's a tangent line. And we need a property. If this tangent line interacts with a radius on my circle, if I have a radius that touches my tangent line, they always meet at a 90-degree angle. So that's the property we need to know. A radius meets a tangent line at a right angle every time. And that's our first property we need to know to do an example. So here's our first example. We have our circle, we have our radius of 5 centimeters. The tangent line is the 15 centimeter line. It didn't extend in both directions, but it's still only touching the circle at one point. And then the instructions are kind of long. Find the segment indicated, find question mark, assume all lines that appear tangent are tangent. That's just because you can't trust the picture and say, oh, this is a tangent line. They have to tell you. So I had to tell you, hey, these are tangent. So we just learned a property that says something happens when our radius meets our tangent line. We know that that is always a right angle. And the reason we need this is because now we have a shape on our circle. We have a triangle on our circle, and specifically it's a right triangle. We like right triangles because we can do lots of things. We can do trig with our right triangles. We can do, we know the angles inside add to 180, but we also know the Pythagorean theorem on right triangles. So all of our tangent problems are actually really Pythagorean theorem problems. It's just recognizing the fact that, hey, this is actually a right triangle. So we can use a squared plus b squared equals c squared. We just have to make sure we identify the hypotenuse correctly. The hypotenuse is always the side across from the right angle. In this case, that's question mark. I can label that as x, just so I have a variable to work with. And I can go plug this into my formula now. A and b, it doesn't matter which order. I can say 15 is A, 5 is B. Or I could say it the other way too. I could say 5 is A, 15 is B. And I go plug them in. 15 squared plus 5 squared. I just have to make sure that I put my hypotenuse in the correct spot. So that hypotenuse could be a number. It could say equals 20 squared or something. I just have to make sure to identify correctly. Now I can square each number. 15 squared is 225. 5 squared is 25. We add those together. We can combine like terms, 250. It is possible that if our number had been on the other side, if our number had been on the right and x had been on the left, we might have to subtract instead of add those together so that we could move it to the other side. And then we just need to know the opposite of squared. Opposite of squared is square root. So we need to square root both sides. We've practiced in the past doing our factor tree and simplifying. This time I would just like you to plug it into a calculator and get a decimal. So if I go plug this in, the square root of 250 is 15.8113, but just go to one decimal place. So I know it's on a circle, but really it's a Pythagorean theorem problem. We just have to recognize, hey, this meets at a right angle. So second, we need to talk about chords. So again, we need a definition for a chord. A chord is a line inside of a circle that does not pass through the center. So obviously, again, I have a picture drawn. There's our chord inside the circle. But we want a property to go with that. We don't just want the definition, we want it to have some math with it. Again, it's how it interacts with the radius of our circle. If our radius hits the chord at a 90-degree angle. So it doesn't have to. If I, for example, had a radius that way, that definitely doesn't hit at a 90-degree angle. But if my radius does hit at a 90-degree angle, it cuts each piece exactly in half of that chord. It doesn't cut the radius in half, it cuts the chord in half. So when a radius meets a chord at a 90-degree angle, the chord is cut in half. So we have two examples. The first one's not actually, or example 2, the first example of our chords, isn't actually even going to use this property, but the second one will. So let's look at example 2. Again, we have a circle. We want to find x. We have a chord drawn in and it's hitting at a 90-degree angle. Now the 8.1 is only this piece until we hit the chord. The x is after the chord until we hit the circle. And then we have our entire radius over here, 14.4. Well, in any circle, all the radiuses are the same length. Doesn't matter where we put it. If I drew a radius going this way, now we have a peace symbol. If I drew a radius going this way, that's also 14.4. Well, they already have another radius drawn in this picture. The green and the blue together, that whole thing is 14.4. That whole thing is a radius. Well, if we're trying to find x, and I know that entire line is 14.4, and I don't want the 8.1, I want the x, but I don't want 8.1. Mathematically, when we don't want something, we subtract. So all I have to do is 14.4 minus 8.1. That's going to find x for me in this case. 6.3. So again, that one didn't even involve this new property we learned, but we will use the new property we learned on the next problem. So one last example. The notes will be pretty short today. Just 3 examples. This one I still needed to label. So we want to find x. And let me label that this hits at a right angle. So again, we want to find x. We have a chord that's cut by a radius at a right angle. So we already know those two sides of the chord are the same. Now the 13.7, it's put in a spot where it's indicating, hey, that's the entire line. So I just have to divide that by 2 to find each side of the line. So 13.7 divided by 2, 6.85. So now I know just one side is 6.85. Then again, we have to recognize I have a shape inside here that can help me. With the x I'm looking for and those two pieces I know, I have a right triangle again. I just do Pythagorean theorem. A squared plus b squared equals c squared. Identifying the hypotenuse is the most important part. Think about which one is the hypotenuse. It's always across from the right angle. X is our hypotenuse. And again, we just go plug these in. It doesn't matter if I put 6 first or 6.85 first. That's a 6.85 in the green. It looks kind of like 6.83. And now I just simplify this. 6 squared, you should know, 36. 6.85 squared, I have no idea without a calculator. 46.9225. I combine like terms. Adding those together, we get 82.9225. I'm not going to simplify I'm not going to round and just go to the 10th until the very end of the problem. So now to get rid of squared, we talked about that on the first problem. To get rid of squared, we do square root to both sides. And now I will just use 1 decimal. Because I could keep going for quite a while. It's 9.106179.221. Just go to the 10th place. Don't forget, we do have a quiz tomorrow. I had misspoken on last notes and said it was last time, but it's actually tomorrow. Quiz is just 4 questions, and you may use your notes on the quiz tomorrow.